Good morning, students. This is the online video tutorials for Physics 5054 O levels. The topic for today is pressure, and my name is Faraz Khan. The learning items for today is pressure and pressure changes. So we're going to be looking at Boyle's law. We're going to see different instruments like manometer and barometer, difference in pressure with relation to depth, and hydraulic brakes and presses. So we're going to understand a lot about pressure in different circumstances. All right, so let's begin with the first set of slides. Um, so what is pressure basically? So let's take an example that you can push a drawing pin into a piece of wood, but you cannot push your finger into the wood even if you exert a larger force. The difference in each case is a different area in contact. The pin has a much smaller area in contact than the finger, hence exerts a much higher pressure that makes the substance yield to the force. Now, you understand that when you're applying a certain amount of force, you have to also consider the area of contact at which you're concentrating all that force. If that area of contact is distributed in a much higher place, uh, the pressure basically decreases. So just as the saying, even if you push your finger into the wood and apply a larger force, you will not pierce through the wood. So it's not, the area of contact is not thin enough to increase the pressure by tenfold. And this is the entire understanding of pressure. It's not just the force itself, but it's also the area of contact at which that force is being applied, which constitutes into pressure. Moving on. So pressure is defined as a perpendicular force acting on unit area of a surface or the force per unit area. P equals to F upon A, P being pressure, F being force, and A being the area. SI unit of pressure is the Pascal or Newton per meter square. It is a scalar quantity. For the same amount of force exerted, the pressure can be increased by decreasing the base area. Given the same area, the pressure can be increased by increasing the force. Now, what they're trying to say is that, let's say you're exerting a pressure um, with a certain force and with a certain area. Now, F is directly proportional to pressure, which means you increase F, you increase P. A, however, is inversely proportional. So you increase the area, you decrease the pressure, you decrease the area, and you increase the pressure. So it's reversed, directly proportional with force, inversely proportional by area. Moving on to pressure in liquids. When an object is immersed in a liquid, the liquid will exert a pressure squeezing the object. When you put a certain object in, let's say, a pool of water, the water exerts pressure from all ends onto that object. So it's exerted evenly across the whole surface of the liquid and in all directions. When you dive into the water is exerting a certain amount of force all across your body. Now, one thing we also need to understand is when we're taking into consideration about pressures, um, we consider liquids and gases both as fluids in the sense that they can change their shape easily. Now, a fluid is a substance that can flow, so when we're taking into account the pressure in liquids, um There are a couple of factors such as the depth of the liquid and the density of the liquid. So we know that the amount of pressure increases uh, inside a body of a fluid with its depth. So as the depth of the liquid increases, as you go further deep down, the pressure on the object increases because of the height of the liquid above that object. All right. Now, like we understood, two certain factors such as depth and density. So the size of this pressure depends upon the density of the liquid, the depth, h of the object, and the gravitational field strength. Now, the gravitational field strength, as we know, is 9.8 or 10, according to whatever the question states. But pressure equals to height into density into gravitational field strength. So, let's say there's a fluid column. What two things are we considering here? The height of the column and the density of the fluid. So P equals to rho GH. So rho is what we call the density. You can see it's a tilted P. All right. Now in a fluid, if 2 points are separated by vertical height, the difference in pressure is the change in P is equals to rho G change in VH. So the only change in pressure comes from the change in height, right? So from the formula P equals to rho GH, we can see that the pressure depends on the depth and density of the liquid and not on the cross-sectional area or volume of the liquid. All right. So hence the water pressure at the bottom of the container in the figure above, like you can see on your screen, will be the same throughout the container as the water level is the same. So let's say you're placing an object. Um, let's say there are four objects all at the bottom right here. The pressure on all of these four objects would be the same because the cross-sectional area of all these four, as you can see, these four little containers, you can say, even though the cross-sectional area of these containers are different, the pressure at the bottom is only dependent upon its height. And so the pressure on all of these four objects are the same. Now, like we discussed, that the cross-sectional area does not constitute for when we're taking into consideration the pressure. The water pressure at the bottom of the container will be the same throughout the container as the water level is the same. The shape of the container does not matter in the computation of the water pressure. And this is the key learning outcome out of this. That even though the objects you can see are clearly different in shape, the pressure at the bottom will remain the same because the height of them is the same. Perpendicular height, like we discussed in the first basic formula, there is the perpendicular force, and so we're taking about height in a straight line, all right? Now, so Let's summarize this. Pressure is basically transmitted throughout the liquid. Pressure acts in all directions. All points at the same depth in a fluid are at the same pressure. Pressure increases with depth, and pressure is dependent not on the shape of the container but on its depth. These were the summarizing points of this topic. Now, moving on to the next, which is pressure in different depths. Now, we understand how height is basically directly proportional to the pressure that is being applied on the object. So, as we go deeper down, the pressure will increase. All right. So, you can see an object immersed in a uniform liquid will experience a pressure which depends only on the height of the liquid above the object. All right. So, atmospheric pressure at the top, as you go down, pressure will start to increase. All right. So, the change in height will give a change in pressure. But we need to also understand that, let's say we've got an object right, let's say we've got an object right here, right? And this is our point, let's say this is our point A, all right? So the pressure at point A would be the atmospheric pressure first plus the rho GH, all right? So I'm just going to use a small p. Just consider this as density, rho GH, all right? And the H would be this height, this height, or you can just extend it till the object, all right? So atmospheric pressure plus the rho GH, H being the height inside the liquid, right? And this is how you're going to calculate the pressure at the object we placed below the line P3, all right? So what was our understanding on this? That pressure, when we're calculating it with increasing depth inside a liquid, we're also going to take into account the atmospheric pressure, and we're going to add that before our calculations of rho GH. Now, for better understanding of the derivation, basically of the hydrostatic pressure, which is P equals to rho GH, let's say we consider a column of water occupying a total volume V and a base surface area of A. The weight of the water is W equals to mgh. We're going to recall that the mass of the water is just the density of the water. So times volume of water, m equals to pv, hence w equals to pvg. And we also know that the volume is a product of the surface area and the height. So v equals to ah. So w equals to pahg. We also know that the formula for pressure is force upon area. Substitute that into W into S. So P equals to rho AHG upon A, cancelling the two A's, we get P equals to rho GH. So this was the derivation for the hydrostatic pressure. Now moving on to barometers. First, we're going to recall our basic understanding of atmospheric pressure. So, like we discussed, air is a fluid, and we're living at the bottom of a sea of air, basically called the atmosphere. So, the weight of the Earth's atmosphere pushing down on each unit area of Earth's surface constitute the atmospheric pressure. Now, we understand when we move on to, let's say, northern areas where there is, higher mountains, and so we understand that the pressure as we move up to the top of the mountain is lower as compared to what it is at the sea level. So atmospheric pressure at the sea level is it's the pressure exerted by this layer of air at sea level, and it is approximately 1.013 into 10 raised to the power 5 pascals. All right, so this value is referred to as 1 atmosphere and is equivalent to placing 1 kg weight on an area of 1 centimeter square. All right, so the pressure at higher altitudes, it's lower than this. So atmospheric pressure at its maximum would be at the sea level, which will be about 1.013 into 10 raised to the power 5 pascals. Now, coming on to the barometer. Um, so usually the understanding is of a mercury barometer. So a barometer is a simple instrument for measuring atmospheric pressure, and a barometer can be made by filling up a long glass tube with mercury, then turning it upside down in a bath of mercury as shown. All right, as you can see it on your screens. So a tube filled with mercury, and then this little, uh, you can use a tray for it, fill it as mercury. All right. The space at the top of the barometer tube is a vacuum and exerts no pressure on the mercury column. The atmospheric pressure pushes against the mercury bath, so upwards. As you can see, the air pressure being applied on the surface of the bath of the mercury, allowing the mercury in the column to move upwards. All right. Hence, the pressure due to mercury column is equal to the pressure due to the atmospheric pressure. The vertical height of the mercury column gives the required atmospheric pressure. From hydrostatic pressure, we know that the P in air is equals to P into the mercury column. So rho GH again, where H is the height of the mercury column, P being the density of mercury, and G is the gravitational acceleration or gravitational field strength. Now we've gone over all of this, but considering this hydrostatic pressure, which is rho GH, let's say we were to find out the length of mercury column at 1 atmosphere. All right. So at 1 atmosphere, as we've gone through, it's 1.013 into 10 to the power 5 pascals of atmospheric pressure. All right. And the density of mercury is 13.6 into 10 to the power 3. So if I was to compute what the height would be at 1 atmospheric pressure, putting it into the formula, P equals to rho GH, P being 1.013 into 10 raised to the power 5 equals to rho 13.6 into 10 power 3 into G 9.8, and we're going to find out the H. All right. So H would come up to 76 centimeters. So the height of the mercury needs to be 76 centimeters for it to have 1 atmospheric pressure acting upon it. So the height of the column is also very important here, and it's also in a straight line. So right, so perpendicular height, like we discussed. Let's say the tube is tilted at some degrees. We're still going to consider a perpendicular height. We're not going to take the tilted height. All right. So height from the bath level, at the top of the bath level, to what it is in the tube. Doesn't matter, the cross-sectional area does not matter if the tube is tilted. Perpendicular height from the top of the bath, from the top surface of the bath to what it is in the tube. All right. So the height remains unchanged if the glass tube is lifted up slightly from the dish. The glass tube is lowered further into the dish. The diameter of the glass tube increases. The glass tube is tilted. The quantity of the mercury in the dish is increased. All of this does not change the height and would still give you the same pressure. So standard atmosphere is the mean atmospheric pressure naturally existing at the sea level on the surface of the earth. As we discussed, it is equivalent to the pressure exerted by a vertical column of mercury at 76 centimeters. If the mercury is replaced by water, the vertical column of water equivalent to the atmospheric pressure is approximately 10 meters, all right? So different densities, different height you're going to get at the same atmospheric pressure. 76 centimeters for mercury, approximately 10 meters for water. And the atmospheric pressure does vary from place to place because obviously, uh, like we understood, different the Earth's atmosphere pushing down on the unit area of Earth's surface constitute to different amount of atmospheric pressure. Now moving on to manometers. Now coming on to the manometers. So it's a simple U tube containing some liquid, which is usually mercury, water, or oil, and we've got a confined gas at one end. All right, which exerts a pressure on our chosen reference liquid in the tube. We've got atmospheric pressure usually at one end. So, and we check the change in levels of height. All right. So the gauge pressure is, as you can see, the change in pressure is P minus the atmospheric pressure equals to rho GH. The pressure exerted by a confined gas changes the levels of the mercury in the manometer. The total pressure of a gas or liquid is the total pressure it exerts, including the effect of the atmospheric pressure. So when the manometer is not connected to any gas supply, the liquid levels in the left and right side of the right side are basically equal. All right. So when one of the tube is connected to a gas supply, the pressure is exerted, and the gas changes the levels of the mercury in the column. Now, if the gas pressure from the gas supply is greater than the atmospheric pressure, it will drive down the liquid level in the left side of the manometer. All right. The pressure of the gas, P gas, can be calculated by P equals to atmospheric pressure plus the pressure of mercury column change in height. P gas equals to P atmospheric pressure plus rho G change in H. Like we've seen here, the unknown pressure from the gas is greater than the atmospheric pressure, right? So it drives the liquid down on the other end, drives the liquid up on the other end. If the gas pressure from the gas supply is smaller than the atmospheric pressure, it will drive down the liquid level in the right side of the manometer. The pressure gas can be calculated by atmospheric pressure minus the pressure of the mercury column change in height. Now moving on to hydraulic presses. So In the hydraulic press, a small force applied to a small piston in a small cylinder is transmitted through a tube to a large cylinder where it presses equally against all sides of the cylinder, including the large piston, which in turn produces a large compressive force upon a stationary anvil or base plate. A pump is used to force the liquid into the cylinder. All right. Now, um, the one major example of this could be car lifts. So when you lift in a car, there's a relatively small force pushing down on a piston on one end, and it's a relatively higher pressure on the other end, which is able to lift the car. Right. So a hydraulic press is widely used in the industry for forming metals. For other tasks where a large force is required, it is manufactured in a wide variety of styles and sizes and capacity ranging from 10 kilonewtons to or less to 100 kilonewtons or more. All right. So different examples, but the one we're going to take a look at is hydraulic brakes. All right. So most brakes act on the rotating mechanical element and absorb kinetic energy either mechanically, hydraulically, or electrically. Mechanic hydraulic brakes are the most common, like those found in cars. They dissipate the kinetic energy in the form of the heat generated by the mechanical friction between a rotating metallic drum or disc and a stationary friction element brought into contact with it by hydraulic or pneumatic means. So, what happens is when the driver depresses the brake pedal, the pedal exerts a pressure on the liquid. This pressure is transmitted via the liquid evenly to the four larger pistons at the wheels. The pressure makes the pistons compress the brake disc onto the running wheels. If the ratio of its area is 10 times, the force exerted at the wheels would be 10 times. So when you press the brake pedal, obviously a smaller area, a smaller piston, you apply a smaller force. But then when it's distributed, it's got a bigger plate um at the brakes. So if the ratio between, let's say, the area 1 and area 2, area 1 being the brake pedal and area 2 being the brake plate or the brake disc, if the ratio difference is 10 times, the force exerted would also be 10 times. Now this brings us on to our final subtopic, which is the Boyle's law. All right. So the Boyle's law states that the volume of a fixed mass of a gas at constant temperature is inversely proportional to the pressure applied to the gas. So what they're trying to say is PV is a certain constant. So if you're going to look at, let's say you're going to compare two, so P1 V1 equals to P2 V2. P1 being the initial pressure, V1 being the initial volume, P2 is the final pressure, and V2 is the final volume. So this is one of the properties that we're going to use when we're going to solve different questions. Now moving on to practice examples. The diagram shows a simple model of the braking system of a car. A force of 20 Newton is applied to piston. As a result, there is a force F on piston Q. Piston P has an area of 5 centimeters square and piston Q has an area of 25 meters square. What is the force F? Now, you've got to understand that pressure on the liquid in the liquid, is the same. The ratio needs to be the same. So if it's 20 Newton upon 5, the other ratio has to be the same. So 20 upon 5 is 4. Now if the area is 25, the force has to be 100 for the ratio to be the same. So 20 upon 5 is also 4, 100 upon 25 is also 4. Now the graph shows the pressure of a fixed mass of a gas varies with volume at constant temperature. What is the volume of the gas when the pressure is 25 kilopascals? So 25 kilopascals we're going to use our Boyle's law. So P1 V1 equals to P2 V2. Just take any point on the graph. Let's say if I take a 1000, um, so P1 V1 is 10 into 100. Now P2 V2 would be, P would be 25, and we can just find V2, which will probably come about to 40. All right. So moving on to the next, a U tube containing water is used as a manometer. When one end of the manometer is connected to a lower pressure chamber, both water levels in the manometer change by 20 centimeter. The gravitational field strength is 10. The density of the water is 1,000 kilograms per meter cube. How far below the atmospheric pressure is the pressure of this chamber? All right, so we're going to do the rho GH for pressure, but we need to take into account that the difference between the height is 20, so it's basically 40 centimeters, and you have to change that unit into meter because the density working is also in meter. So apply the rho GH on this, 1000 into 10 into zero point 0.4. All right, 0.4 meters. We're not going to take centimeters on this. Make sure that your units across the entire formula are the same for everything. So if it's meter on 2 units, on 2 identities, it has to also be meter on the third one. You cannot use centimeter on one and meter on the other 2 identities. All right. So it would probably come out to 4,000 on this one. All right, so the base of a rectangle storage tank is 2 meter by 3 meters. The tank is filled with paraffin to a depth of 3 meter. The density of paraffin is 800. Gravitational field strength being 10. What is the pressure at the bottom of the tank? You know the cross-sectional area is not taken into account. So 3 into 2, the square base means nothing. So we're just going to do the rho GH on this. And so 8,000 into 10 into 3, the height. We're not going to take the quantities of base area on this. All right. Moving on to the next, the diagram shows a simple manometer that contains a liquid. Side X is connected to a gas supply of pressure R. Side Y is open to the atmosphere at pressure S. Which pressure is the length H used to measure? So when the gas supply is greater than the atmospheric pressure, as we discussed, when the gas supply is greater, it drives the mercury upwards. We're going to add them, all right? So R plus S, P atmospheric pressure plus P mercury is what we did in the previous slide. So mercury being uh, the gas supply one, all right? 4 different liquids are poured into identical measuring cylinders. The diagrams show the depth of the liquid and their densities. Which liquid causes the largest pressure on the base of its measuring cylinder? All right, so rho GH, will remain the same. You've got different heights and you've got different densities here. So you can find out which one has the greatest. So 2 into 10, 20 into 1.6, 30 into 1.2, 40 into 0.7. And whichever is the highest number will be giving the largest pressure on the base of its measuring cylinder. All right. 5 blocks of the same mass but different base areas. They all rest on a horizontal table. The graph is plotted to show the relationship between the pressure exerted on the table and the base area of the block. Which graph shows the relationship? So like we discussed, pressure equals to force upon area being inversely proportional to pressure. So area increases, pressure decreases, but not linearly, decreases exponentially. So D should be the answer for that. Thank you so much. If you've got any questions about this topic, put them down in the comment box below and I will reply to them. Thank you so much. Happy learning.